This video is sponsored by Siemens EDA.
In this video, I'd like to show you how you can perform a DC drop analysis and simulation using Siemens EDA HyperLynx. For this, we will use this USB Ethernet adapter demo board. I'll show you the process of exporting ODB++ data and what you need to pay attention to in Altium Designer and importing that into HyperLynx, and then performing DC drop analysis on a 3.3 volt net that feeds various polygon pores through vias, through decoupling and bypass capacitors into the USB Ethernet physical layer. Performing DC drop analyses are incredibly important to make sure you stay within certain voltage ranges and levels, but also that you don't exceed current densities within your design, which could cause thermal issues and failures. And also lets you analyze and optimize the placement of your traces, your sizing of polygon planes and pores, as well as how many vias you might need to distribute current and power throughout your design and how that current and power is actually distributed within these various vias, traces, and planes. With that being said, let's have a brief look through this design, this USB Ethernet adapter PCB that are designed for an upcoming Altium Designer course. As the name implies, we have a USB port on the left-hand side. This is a USB 3 Type B connector. We have a USB Ethernet adapter physical layer IC in the center by microchip, and on the right-hand side, we have this gigabit Ethernet mag jack. The physical layer right in the center is pretty simple to interface with. You just have to follow the datasheet and some app notes. And more importantly for this video, it only requires a single input voltage rail at 3.3 volts to power the physical layer. This physical layer actually generates its own internal voltages in addition as well. But what we want to do in this video is perform a simple DC drop analysis just on this single rail to see if there might be any DC issues with the current that this device, this physical layer draws, and if we get outside of our 3.3 volt margin, the way this PCB is routed through vias, through traces and planes, not taking any AC effects into account. Our original power source is from the USB, so from the host device that connects to this USB Type B jack on the left-hand side. We have a simple 3.3 volt step-down or switching buck regulator that generates our 3.3 volt rail. At the output LC filter, we have 4 vias via this little planelet that feed onto the bottom layer, and that distributes this 3.3 volt rail and 3.3 volt net throughout the PCB. And again, we dig with some vias to the top of the board again through our decoupling capacitors into our physical layer. So that's what we're going to be performing the DC drop analysis on. This is a very simple demo board, just so we can look at a single rail and see how to set that up in HyperLynx and how we can analyze the results. The schematic for this, as the PCB is very, very simple. We just have a couple of components. For this video, we are just interested in the power path. So again, looking at the USB Type B connector, we go through a placeholder Pi network, so capacitor, series element capacitor, which we can adjust depending on our requirements. That then feeds at the top this 3.3 volt switching regulator, and this 3.3 volt output then feeds the various power pins we can see at the top with this physical layer schematic symbol. So pins 20, 26, 39, and 38 are the input voltages of 3.3 volts. We can see the relevant bypass and decoupling capacitors in the top left. The 2.5 volt and 1.2 volt rails are generated by this PHY itself, and we won't be concerned with this in this video. We just want to analyze the 3.3 volt rail. When you're about to perform any type of simulation, I'd strongly suggest naming all of your nets in your schematic. This will make it far easier then to find the relevant nets you would like to simulate, be that for DC or AC power analysis or for signal integrity analysis, or for instance high-speed nets. This is my typical practice, and what I do for every single schematic that I design is that every single net gets its own net label. For instance, here we can see the USB, high-speed and super-speed differential pairs, but even the nets that I might not use, if I zoom in, I've labeled even the unused nets in this design. And I find this is very, very important to maintain consistency across your projects, but also this will help you out when sorting out the nets and which nets you want to simulate later on, as we'll see. Also for power nets, I find this is very important. So for instance, all my positive rail power nets, such as 3.3 volts or 2.5 or 1.2 volts, I add a plus sign at the front of this net label or this power flag. And very easily later on in HyperLynx, we can see when we sort alphabetically our name, all our positive power nets will then be grouped together. If you have negative power nets, just putting a minus in front will help with that as well. Other than net names, it's also incredibly important that you have proper component designators in place, that you don't have any duplicate designators. Every item is unique and sensibly annotated. This is important because this information, for example, that this capacitor is designated C1 or this resistor is R5, this is incredibly important because this will be included in the ODB++ export board that will be then used in HyperLynx to assign, for instance, certain models to capacitors or voltage regulator modules and so on. So make sure your components are properly annotated and designated. This is some sort of minimal preparation you'd want to do on the schematic side to make sure your exports are clean. This is of course tool dependent, but I'd strongly suggest setting up your layer stack and your build up properly in your tool. For instance, in Ultimate Designer, I can go to Design and then Layer Stack Manager, and this lets me edit all of the layer information. So that could be layer type, if it's a copper layer, if it's a prepreg or a core layer, what the material properties are, for example, copper thickness, or for instance, the thickness of the dielectric, as well as the dielectric constant on all of these other parameters. So in Ultimate Designer, this is what I've set up, and these are based on my manufacturer specs, and these can be useful later on for AC analysis, for signal integrity analysis. Also, in part, some of this information might also be used for the DC drop analysis. For instance, the copper thickness could of course be important. So make sure you have that set up in your tool if your tool allows, because that information can be included in the ODB++ output format that we'll be generating in just a second. So we are now ready to generate our output format. So rather than generating Gerber files, which don't contain terribly much information, they are just essentially layer information for the copper layers and silk and solder mask layers, we want to include some other information as well, such as net names. We might want to include this layer and build-up information that we just saw. And for that, the preferred data format, or very easy to use data format, is the ODB++ format. And you may have used that before to get your PCBs manufactured and assembled. The ODB++ format contains far more information than just the plain Gerber files. Now, pretty much any ECAD tool should be able to export this format, so it's very widely available and can be used very easily then with HyperLynx. In Ultimate Designer, I can go to the top left file, Fabrication Outputs, and again, we're not exporting Gerber files, we are exporting ODB++ files. For this, there are a couple parameters you have to pay attention to. One is, of course, that you've exported the right layers. In particular for us, of course, the copper layers are most important for this design. So I have all of my 4 layers. I've got my signal, ground, signal. You can, of course, export the top overlay, bottom overlay, the solder mask, and so on, as well as the drills are important for the vias and plated through-hole pads, and of course, the board outline as well. On the left-hand side, we can keep most of this as default, but pretty much all of the default parameters typically are okay, but make sure you double-check them, and then click OK to export the ODB++ files. After the ODB++ files have been generated, we can use the Camtastic view, at least in Ultimate Designer, then to look through the layers to make sure everything has been exported correctly. And this is a step I will do for simulation, but also, of course, for manufacturing, just to make sure that my layers are correct. And I quite like having different views of the PCB because it lets me spot errors. But just make sure all of your layers and correct files are in there, and then we can move over to importing into HyperLynx. Now, having exported our ODB++ archive, I've opened up HyperLynx SIPI, and we can import this ODB++ file, and you can see the import is actually a very, very simple process. All we have to do is go to Browse on the left-hand side, then we want to open our ODB++ data folder under Board Sim, as we can see in the second row. Navigating then to our output directory, I simply select the ODB folder. You will typically get these warning messages. For example, here, illegal 1-pin components are converted to test points, and that's exactly the correct thing to do because we have several test points in this design, and HyperLynx is just notifying you of that. The next warning will typically appear as well. This may be to do with artifacts that some traces are not directly connected to the direct centers of pads, and therefore HyperLynx might throw this warning thinking these traces are not directly connected, although they are. They might be coming in from a somewhat funny angle or not hitting the center of the pad, but typically you can safely ignore this warning, and you do not want to connect them using virtual Manhattan style routing because that can take some length of time. So for now, assuming you've checked your design, you can just click on No. And that's how quickly now we've exported our ODB++ files and imported them into HyperLynx. We can see our board view right here. Middle mouse button, I can move around and scroll around. Middle mouse wheel, I can zoom in and out, and we can examine the nets. We can also examine the components. We can see here C13, C14. So this ODB++ file format contains several bits of useful information rather than just the layer information. We have several toolbars in this HyperLynx view. We will be mainly concerned with the toolbar on the left-hand side. If we go to the left-hand side, we can see this kind of top to bottom view. So we might want to start with a design setup, then we want to assign some models, then we do the simulation setup, then we work our way through these various simulation environments. So it's a nice top to bottom kind of workflow. Of course, you can skip some steps if you're not interested in signal integrity. You can jump right over to power integrity, for instance. What we will be doing is first of all starting off with a design setup. So I'll click on design setup on the left-hand side. And the first thing you would typically want to do is verify that the stackup has been imported and assigned correctly. So if we go to edit stackup, this new window opens. And again, this is information that was exported using this ODB export and imported into HyperLynx. So we don't have to manually enter these parameters again and again. It's nicely exported and imported. So make sure your layer assignments are correct, that our thicknesses are correct, and there's some neat features in this tool, for instance Z0 planning, which of course has to do with controlled impedance, so you can have HyperLynx calculate the required trace widths and trace spacings, for example, for differential pairs to hit certain target impedances. And we might look at that in a future video when we're doing signal integrity analysis. For us now, for power integrity, for doing DC drop analysis, this isn't terribly important for now, but there are many cool features and tools in HyperLynx that can make your life quite a bit easier. In any case, we've now verified our stackup looks okay, our input looks okay, so we can just close this window. Again, in design setup, for power integrity, we might want to now set up our power supplies. So we can set up power supplies, we can set up our interconnection of power networks, for example, going through series elements, going through VRMs, voltage regulator modules such as buck converters or linear regulators, and so on. If I click on power supplies, we can see HyperLynx has automatically selected what it thinks are the power supplies in this design. And again, this goes back to my point of labeling nets appropriately. It's picked out the nets which have a plus in front of them, so plus 1v2, 1v2a, 2.5, 3.3, but also typical nets such as the ground or the reference net. You can, of course, look through if there are any other power nets here. You can just check them and then add them to the design. And on the right-hand side on the bottom, you can then assign a voltage just by typing in a certain voltage there. But of course, we actually have all of our nets in there already, and HyperLynx has automatically figured out, because of the sensible net naming, what the voltages are at. And of course, ground is our reference, so that's 0 volts. After having added and checked the power supplies, we can move now over to the right-hand side, still in the design setup submenu, looking at the power network setup. So if I click on this, a new window opens. We can see our identified power supply nets. And if I click on one of them, for example, 3.3 volts, we can see again from the ODB++ extract what the 3.3 volt net is connected to. We can see U2, and U2 happens to be our physical layer. So that, of course, is tied to 3.3 volts because we have various pins, 14, 20, and so on, attached to 3.3 volts. But we also see L1 and U1. And this is, of course, tied to 3.3 volts because this is the output of the switching regulator. This was our buck converter and our series element, our series magnetic element L1, which actually generates our 3.3 volts from our 5 volt input supply. But U2 is our only 3.3 volt current sink in this design. Now, if I click on U2, a new window opens. And what we want to do is, of course, assign how much current draw is being caused by U2. And we can do this either for the whole part as a single unit. So this U2 draws, let's say, 500 milliamps of current, or we can do it on a pin by pin basis. So now here, HyperLynx has shown us U2 as a power component, as well as all of the pins that are tied to 3.3 volts. And of course, this is important because you might have some sort of configuration pins. Some might be strapping pins, which you have to tie high or low, but they don't actually sink or source any current. For instance, going back to the schematic, let's say R6 wasn't here and we tied 3.3 volts straight to pin 35. Pin 35 would still show up as a power pin, so you have to be careful of what you choose as pins that actually sink or source current. But in our case, we don't have any of these pins being strapping pins. They are actually all power pins. So I can either select them individually by clicking on the left little box where this arrow appears, and the right-hand side, because we're interested in a DC drop analysis, we want to assign a DC sync model. So I can click on assign, and then this little window pops up. And of course, you can do that for groups of pins. If I click on cancel, I can control click and I can select individual pins and then assign them a generic DC sync model. What I want to do is actually select all of them, so I'm just going to click and drag and assign a DC sync model to all of those pins. So they're all selected, right-hand side, click assign, and now we can have that option of either we apply our current sync model to each sync pin or to the whole combined group. I'm going to select each sync, and on the right-hand side we can see the equivalent model. We have a current sync with some parallel resistance. The parallel resistance for now we will just keep as the default value, but the sync current per pin I'm going to change to 50 milliamps, so 0.05 amps. Click OK, and we can see now the model has been assigned to each individual pin, that each individual pin sinks 50 milliamps of current. Now, of course, you should check the datasheet, app notes, and any manufacturer guidelines to see what the actual current sync is per pin, if that is even given, is of course the other question. But typically in the datasheet you might find an overall current draw given specific operating conditions. So then of course you might want to use that whole group DC sync model. In any case, now we have to find our power supplies, and we've created a very simple sync model for the pins on U2, which is our physical layer. So I can click OK, and now we can see here our VRM, our power network, has now been updated. Other than, of course, our current sinks and our power sinks, we need a power source as well. And HyperLynx here has already identified that this network might be feeding from U1, our buck regulator that actually generates the 3.3 volts, through the series element L1, which is part of our switching regulator. So we want to create a power source. The way we can do that, let's just click on U1, for instance, and then on the right-hand side, click on VRM Manager. In the VRM Manager, we will click on New, and then we want to create a new VRM, so voltage regulator model. The first thing we want to do is, of course, assign the voltage, and our voltage is 3.3 volts. And now we can choose the model type, either simple or advanced, and we'll stick with simple for now. There are two types of models. One is an AC model, shown with the equivalent circuit where I'm circling my cursor, and to the right of that, we have the DC model. In our case, we are only interested in the DC model for this particular video and this particular simulation. Now keep in mind, this AC model, for instance, might be a bit misleading because you might think the value of L, the inductance, is simply the output inductor of the buck regulator, but it isn't. These equivalent models for AC and DC are the output impedance of the regulator you are using looking back into its output ports. The impedance you measure and then you model with R's and L's rather than the actual physical value of components. That's very important to know. But in any case, we need the DC model. We want to assign a power net, and that's going to be 3.3 volts. Our power pin, for the sake of the simulation, we are not going to be concerned with U1. We are starting our voltage and power source from the output inductor, the second pin of the output inductor. And that happens to be L1 pad 2 or pin 2. That's our 3.3 volt net. Our reference net is ground. Now, of course, the inductor itself doesn't have a ground reference. It just has the switch node and the 3.3 volt node. R and L are to do with the AC simulation, so we don't worry about those, but we worry about RDC. And just as a rough estimate, I'm going to type in 10 milliohms of DC resistance for our simulation. Then I can click OK, and we've created our new output model. We can click Close and click OK. With that in place, we can see our power network, our power tree is updated. We can see new voltage power source, which is the output of our buck regulator, which now feeds our 3.3 volt supply system. And then we have our current and power sinks, which are the power pins of U2. Now we can click Apply and Close. Now with all of this set up, we've now set our pin 2 of our inductor as our 3.3 volt voltage generator. We have this small polygon planelet connected to 3.3 volts, and we have a couple of vias that go from layer 1 to layer 4 and feeds this somewhat small polygon pore for 3.3 volts. We can dig up through some vias, feed through a decoupling capacitor into the relevant pins of our physical layer. So that's what we want to simulate. What voltages, what DC voltages do we see at these relevant power pins? What current densities do we see? And is our design okay, at least at DC? And that's what we'd like to simulate next. And for that, we go to the left toolbar again and going to Power Integrity. Then we can select DC Drop Analysis. This new window opens and we can see a couple different aspects to this. On the top left-hand side, we can see all the power nets that we created and selected and identified. If I go through them, we can see also on the right-hand side that the relevant copper features and components are highlighted that belong to that specific power net. For instance, 3.3 volts, we can see on the left-hand side, we have our power source, which we defined as the output inductor of our buck regulator. 4 vias feed the bottom polygon pore, and then we go up through vias again to layer 1 to the various decoupling and bypass capacitors into the physical layers, and we can zoom in and see all the relevant power pins that we selected. This is a good way of verifying that you've set up your simulation, at least your sources and sinks, somewhat correctly, just visually. On the left-hand side, we can also see all of the assigned models for that particular net that we selected. We have our output inductor, and if I click on this, we can see on the right-hand side, this is actually highlighted, and we can select and see the various power sinks that we created and defined. So all of these 50 milliamp pins that belong to the physical layer. Now we can add in some constraints that when we run our DC drop analysis, we don't exceed certain specifications. That could be the maximum voltage drop allowed in percent, how much via current we allow per via, what the maximum current density is at any cross section. In addition, we can add in some sort of power constraints, so what the power loss at IC pins is and per layer and so on. So that can also help with some thermal analysis. When performing the simulation, HyperLynx also generates some very nice reports. HTML reports that shows pass-fail results, show where these fails happened, and more. I'll keep all of these settings as standard. Of course, it depends on your design. So before we run the simulation, on the bottom right-hand side, you can see we can run a DC drop simulation, we can run a resistance calculation and simulation, or we can run both. I'm just going to run both for now and click Simulate. That didn't take terribly long and we're already greeted with our report. This is the HTML report that we selected to be generated, and here we can see our pass-fail results. And for the settings we set up, this rather low current draw, we can see our max voltage drop has passed with a constraint, and we can see by how much our voltage drop actually occurred, and that's only by 1.4 millivolts. We can check our max current densities, our maximum via currents, power losses, and power densities. So this is a pretty cool, simple report that you can use for documentation later on as well. Other than the summary, we also have the voltage and current drops. So we can see graphically the areas of voltage drops. And of course, we don't have terribly much voltage drop here, so the colors might be rather extreme compared to the actual voltage drops we get. Current density analyses, how much current the VRMs have to source, how many sinks we have and how much they are sourcing, and what voltages appear at the relevant power pins. And again, this is just a DC analysis. Closing all of these reports, we can also open the power scope, which I think is quite a cool feature, which again is in our DC drop analysis tool or setup window. If on the right hand side, click on show power scope, expanding this window a tiny bit, this is actually a 3D view, which I can rotate around. And this is a kind of waterfall representation, for lack of a better word. If we look at the scale on the left-hand side, the blue, darkish blue is 3.3 volts, and going into red is our maximum voltage drop. So we go from 3.3 volts to, just under, we were only dropping 1.4 millivolts in the simulation. The lower we go in this 3D representation, the more voltage drop we have at. And this is also a physical geometrical representation. If we look from the top down, we can see the 2D representation. Starting on the left-hand side, we have our DC power source from our inductor, going through the planes and going to the various IC power pins, vias, and pads. So as expected, from our power source, we don't have any voltage drop, but as we traverse through this power distribution network, we're getting more and more voltage drops depending on the geometry, copper sizing, and current draws of our design. On the right-hand side, I can click on visual options, and we can change our graph type from showing DC drop voltage to, for instance, showing the DC current density. So depending on where we have peaks, we have the highest current density. So depending on if you have very current dense areas, you might want to increase your trace widths, you might want to parallel planes to make sure your current density is within reasonable amounts. And we can see exactly where those high current densities happen. For instance, layer transitions, via transitions, compared to just having solid white planes. We can also look at the DC via current on the right-hand side. We can see that, for instance, if we parallel 4 vias, the current isn't shared equally across them. Here, for instance, for the 4 vias that come from the output of our DC voltage regulator that feed the planes, the current distribution between these 4 vias, we might expect them to be one via carries a quarter of the current, but here we can see there's actually this somewhat non-linear distribution of current, which you might want to optimize in terms of via placement. We can also look at DC power density. We can look at the DC current vectors, which is a quite nice representation of our current flow from our power source to our various power sinks. Now, of course, this is a very simple low current, low power design, but you can imagine how useful this is to verify DC voltages. For instance, if you're creating an electronic speed controller for a motor, or if you have very high current demands, you have to make sure that your DC drop is within acceptable limits, that your thermals are within acceptable limits, and you can use HyperLynx to do that very, very quickly. This, of course, is just scratching the surface of what HyperLynx is capable of, and in future videos we will be looking at other power integrity tools, such as looking at AC analysis of this design, seeing what our decoupling capacitor placement looks like at AC, if there's anything we can optimize, and of course we will use HyperLynx signal integrity tools to simulate the signal integrity of these high-speed and super-speed USB 3 links, as well as, of course, the gigabit Ethernet links on the right-hand side of this physical layer. Again, we've only scratched the surface of what HyperLynx SIP is capable of, and I'd like to give you a few more introductions to the tool and what is possible with this tool in future videos. Thank you very much for watching this video. I hope it was helpful, and I hope it gave you a brief introduction into HyperLynx, how to export ODB++ data and import it into HyperLynx, and perform a very basic DC drop analysis. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, firmware, DSP, and embedded systems videos. Thanks again for watching, and I hope to see you in the next one. Bye-bye.